Okay, welcome back, everyone. So maybe before we begin, a quick note about the Kaggle competition. So we will be starting the Kaggle competition very soon. I think the official start date is Monday, but we are trying to open it up before Monday. And as some of you might have noticed, there is actually an option to go find your teammate in Piazza. So there's this tool called Search for Teammates. And I see that at least 7 to 10 teams have already done that. And like you are in the process of finding your teammates. Like, so if you don't have, you have to be a team of 3. So if you don't have teammates for your competition, like go try to post an ad in Search for Teammates in Piazza. And like as soon as we open the competition, I think we will have a Google form which you need to fill with all the information about your 3 teammates. So start searching for your teammate if you haven't done it already. Okay, so I think we can start. Let me share my iPad. Just one second. Okay, so we are continuing our discussion on ensemble methods. Okay, so just to give you some idea, so in the previous lecture, we discussed about bagging, right? Bagging classifiers. The basic idea behind bagging is you create k different data sets by using bootstrap method, and then you train k different classifiers, right? And then you get the predictions of these k classifiers and do majority voting if you're doing classification, or just take an average if you're doing regression, right? So, and we also learned that bagging reduces the variance, right? And we looked at variants of bagging for decision forests, which were random forests and extremely randomized trees, right? Okay, now this is the first ensemble method. Okay, so now we are going to look at 2 more ensemble methods. And the second one that we are going to discuss now is the idea of boosting. So this was introduced by Freund and Shafire in 1996. Okay, so this is one of, at least for me, this is one of the really elegant learning algorithms out there. Okay, so this is a very powerful technique which is going to combine a bunch of base classifiers. Okay, so maybe let me first explain the basic idea of boosting with some illustration, and then we will get into the algorithm. So the basic idea is kind of similar to bagging in the sense we are going to have k different classifiers and we are going to combine these k different classifiers. Okay, but the way in which we are going to do that in boosting is a bit different. So what we will do is we will take our data set, okay, and train the first classifier using the data set. Okay, so now after training the first classifier, you look at all the errors that this first classifier has made. Now you reweight the data set based on classifier 1's performance and create a new data set. It's just the same data set. It's not a new data set. It's just the same data set. But initially, all the examples in the data set had 1 by n weight, okay, weightage. Now you just increase the significance of the examples and train a new classifier, C2, using this data set, okay? So now this new classifier might make some mistakes, right? Now, looking at the mistakes of this new classifier, you're going to reweight the data set again in such a way that whatever examples where C2 was making mistakes, you increase the weight of that and decrease the weight for examples which already C2 is good at classifying. Okay. Now you use this to train a new classifier. Okay. So now what is happening here? So what is happening here is the second classifier is trying to rectify the mistakes of the first classifier. And the third classifier is trying to rectify the mistakes of first and second classifier. Okay. Now this is a bit different from bagging in the sense this is actually a sequential process. So it is not like I train all the 5 classifiers. If I have to do 5 classifier boosting with 5 classifiers, it's not like I'm going to train all the 5 classifiers in parallel. Okay, so I'm going to do them sequentially. First train the first classifier, whatever the performance, like based on the performance, like if there's an example which is hard for C1, then you increase the importance of that example for C2. If an example is easy for C1, then you reduce the weight for C2 because C1 is already good in predicting this example. I don't need C2 to waste time on doing this prediction. Okay, so that is the basic idea. So now once you train these sequence of classifiers, now you combine these classifiers together with some weight. So let's just call them as alpha 1, alpha 2, alpha 3. Okay, so now you combine these classifiers as the final prediction. So the final prediction, let's just call it as ym of x, which means there are m models. Okay, now this is given by sine of summation over m is equal to 1 to capital M alpha m ym of x. Okay, where maybe to make things easier, like I'm going to call these classifiers as the first classifier as y1 of x, the second classifier as y2 of x, third as y3 of x, and so on. These are my classifiers. Okay, now this is the basic idea behind boosting. So there are so there are a few questions in the chat, and I think these are all really good questions. So this is what answering these questions is this lecture. So to give you some idea for others, like, so I think, what do I mean by hard and easy? Okay, we are going to look at it. And can you explain more about how the data set can be reweighted? That's more details about the algorithm. We are going to look at it. And what if C1 overfits? That's also a good question. So we are going to look at all these questions, but this is just to give a brief idea of like how the whole boosting process is going to be. Is it clear? Okay, so now let's get into the details, right? So there was this question, like, what if C1 overfits, right? So typically in boosting, like, so what we would do is like all these base classifiers are going to be weak learners. Okay, so what do I mean by weak learners? So you don't have like an over parameterized base classifier. Your by base classifiers, so the beauty of boosting is your base classifier, all that it requires is that the base classifier has to be only slightly better than random. Okay, even if you have like a really bad classifier, like which is just slightly better than random, you boost a bunch of those classifiers, you will actually get a very strong classifier. Okay, now that is the power of boosting. So normally you go with weak learners. Okay, and how are we going to weight things? We are going to discuss about that in detail, but the basic idea is if a data point is correctly classified, okay, then reduce the weight. And if the data point is misclassified, then you increase the weight. Is that clear? Okay, so we will look at an example like after we go through the details of the algorithm. Okay, Okay, so now that's an abstract explanation of what is boosting. So now let's get into a very specific concrete problem. So I think that's what Masood means by example. So we're going to consider a two-class classification problem. Okay, where I have, let's say, n data points, xn, tn, n is equal to 1 to capital N. Okay, where tn is given by either -1 or 1. Okay, so what we are going to do is initially the weight wn is the weight for example, nth example. Okay, so initially the weight for the nth example is going to be 1 over n. What does that mean? If I have 100 examples, all the 100 examples are weighed uniformly, like 1 over 100. Okay, so now this is normal classification task, right? Like, so you have all the examples, same weight. Now you learn a classifier. You could use any classifier that you have learned. For example, let's say we do logistic regression. Okay, you train a logistic regression classifier by using this data set where the weightage for each data set is 1 over n. Okay, now how do we proceed from there, right? Like, so we are going to look at one specific version of this boosting algorithm called AdaBoost, okay, or adaptive boosting. Okay, so how does that work? So first you initialize the data weighing coefficient Wn by setting Wn1, like when I have the square bracket 1, that means for the first classifier. Okay, Wn1 is equal to 1 over n. For n is equal to 1 to n for all the examples. Okay, now for m is equal to 1 to capital M, whatever number of classifiers you want. Okay, we are first going to fit a classifier. Fit a classifier ym of x, okay, to the training data, okay, by minimizing the following weighted error. Okay, so my error function Jm is going to be summation over n is equal to 1 to capital N, the weight associated with the example, and the indicator if it is wrong. So is not equal to T of n. Okay, now this is just an indicator function. If the prediction is not equal to T of n, then this is 1. Otherwise, it is 0. Okay, so now my loss is just the weighted error that the classifier is making. Okay, now once you train and fit the classifier, then we are going to evaluate a couple of quantities. Okay, first is epsilon m. I'll explain what is epsilon m. Epsilon m is basically summation over n is equal to 1 to capital N, Wn of m, indicator, okay, divided by summation over n is equal to 1 to capital N, Wn of m. So epsilon is basically representing the weighted measure of the error rate, okay, of each of the base classifiers. So this is just the error rate, because if the numerator is sum of weight for all the misclassification divided by sum of all the weights in the data set, right? Like, so this is just the error rate, okay? And we are going to use this to evaluate alpha m, which is basically ln 1 minus epsilon m by epsilon m. Okay, now next step, we are going to update the data weighting. Now we are going to update. Now this alpha m is basically the weight given to this classifier. Okay, so then we are going to update the data weighing coefficient for the next step in the process. For the next classifier, m plus 1th classifier, the weight is given by the previous weight multiplied by exponential of alpha m, indicator ym of xn not equal to Tn. Okay. Now, what does this mean? So every time there's a mistake, then the weight is scaled by exponential of alpha m. If there is no mistake, then this is e power 0, so 1, right? So if there is no mistake, the weight stays the same. If there is a mistake, only for those examples, the weight is increasing. Is that clear? Okay, now you just repeat the process. Now you go back, do the next second classifier, evaluate these, set the weight for the third classifier, and continue, okay? Now, after finishing all the M classifiers, finally, like you can decide your class, you can construct your ensemble method, which is ym of x is given by sine of summation over m is equal to 1 to capital M alpha m ym of x. Is that clear? Okay, so you might have a few questions here. So why is alpha m, what is the epsilon m and what is alpha m, right? Like, so why does this weighting scheme, why is this a correct weighting scheme? Why should it help us, right? Like, so to do, like, this is the algorithm, but we are going to see how to come up with this algorithm as the next step. But for now, I would like to repeat the process. So the idea here is initially all the examples are going to have same weight, okay, 1 over n. Then for every classifier, you will first fit the classifier by using this weighted error function. Then you evaluate the error rate and use the error rate to compute alpha, which is the coefficient for the classifier. Then you update the data weight for the next classifier with this formula. So this formula is basically increasing the weight for examples where this classifier has made some mistake, okay? Now you repeat this process for m times, and finally you have collected all these alphas, right? So the classifier is given by alpha times y summation over all the classifiers, okay? Is there any questions about the algorithm before we see an example? Any questions? Chat, hand raise. Okay, so if there are no questions, then, okay, so there is a question. Okay, so what is indicator? Okay, so indicator function is just a function which is equal to 1. So indicator of ym of xn is equal to t of, not equal to t of n, right? So it's just equal to 1 if this condition is true, if ym is not equal to t of n, okay? So I'm just, it should be ym of x of n, okay? And it is 0 if 0 otherwise. Let's just see otherwise. So when I say indicator of a condition, whenever the condition is true, it's 1, and otherwise it's 0. Okay, so I said weak learner. What do I mean by that? By weak learner, I just mean that you could have like a algorithm which is not performing very well, like a very simple algorithm with very high bias. I will actually give you an example for a weak learner right now. Okay, so now let's actually do an example. So we are going to consider boosting, okay, where the base learners are just threshold on one of the input variables. Okay, so this is like a very simple classifier. Okay, this classifier actually has a name. It's called decision stump. Okay, so what is decision stump? So this is a very simple classifier. Like, let's say I have theta 1, theta 2, theta 3, 3 features. Okay, now, okay, so maybe it's misleading. Thetas are, we use theta for parameters. So let's just call them as, let's just call them as x1, x2, x3. Okay, I have 3 features, okay? Now this classifier will randomly pick one of these features, let's say x2, and just put a threshold on it. So if x2 is greater than some threshold, then it is class 1. Otherwise, it's class 2. This is my classifier. Okay, this is a very simple classifier. Okay, now I'm going to take a bunch of such classifiers and construct a very complex classifier from this. Okay, so here is the example. So in this case, you can see that there are two features. Okay, so let's just call this as x1 and this as x2. There are two features, and my goal is to come up with a classifier which will divide blue circles from red circles. Okay, now the black line, right? So the black line is the decision boundary for my most recent classifier. Okay, and green line is the combined decision boundary so far. Okay, and the radius of these circles here are actually the weights. So now you can see that, so this is my first epoch. Okay, now first classifier, I'm constructing the first classifier, and you can see that all the circles are of same radius, so all are equally weighed, and the green line that you're seeing is same as the red black line, like so, because there's only one classifier so far, and that is dividing the data like that. Okay, now you see that anything to the right should be red color, anything to the left should be blue color. Okay, so now we actually see that there are these wrong blue examples which are misclassified, right? Okay, so I don't know how to highlight them well in the presentation. Okay, let's see if this works. Do you see the highlighting? Okay, so now there are these blue lines, circles which are wrongly classified. Similarly, there are these red circles which are also wrongly classified. Now you can see in the second classifier training that these things are magnified, because now we are going to give more importance to classifying these big circles correctly. Okay, you can see that the correct examples weight has reduced, incorrect example the weight has increased. Now you learn a second classifier. The second classifier is actually this black classifier. When you combine the first and second classifier using the alpha, you get this complex, not very complex, but already nonlinear green line, right? So now you do the third line, the third classifier. This is the third classifier. Now this is the fourth classifier. This is the fifth classifier. This is the sixth classifier. As you keep learning, you can see how the size of various examples evolve, and also how the decision boundary is getting more and more complex. Okay, now this is very interesting because we started with a simple linear model, which is not even a fancy linear model. It's just a thresholding model. And with such a thresholding model, we can actually boost a bunch of them and get a very complex decision boundary. Okay, so now that is, this is like a practical example of how boosting works. So alpha is always a linear combination. Yes, alpha is always a linear combination. Okay, so now that I have motivated the algorithm, so now let's actually go to first principles and see how to come up with, like how did we come up with these alphas and epsilons and weighing scheme, right? So to do that, I'm going to introduce a new error function. But maybe before that, a quick quiz. So what are the various error functions that we have seen so far in this lecture, like in this course? People can probably post it in, you can type it in the chat, or if you want to answer, you can also raise hand. Okay, 0-1 loss, MSE or squared error. Okay, what else? Hinge loss, cross entropy loss, which is the logistic regression error. Like, yeah, I think these are pretty much the error functions that we have seen so far, right? So now we are going to look at, to explain how boosting works, we need a new type of error function. Okay, so which is the idea of exponential error. Okay, so let me first define the exponential error function. As the name suggests, it is just the exponent of the error. Okay, so it's E is equal to summation over n is equal to 1 to capital N, exp of minus t of n fm of x of n. Okay, now this is my error where fm of x of n is my boosting classifier, which is basically summation over L is equal to 1 to m alpha L YL of x. I'll just add a 1 over 2 for mathematical convenience, okay, where t of n belongs to minus 1, 1. Okay, now what does this error function mean, right? Like, so if you look at this error function, if you have correct classification, whenever there's a correct classification, both +1 or both -1, this term is going to be 1, right? So the whole term is -1. On the other hand, whenever you have a wrong classification, for example, if this is 1 and this is -1, in which case the total is minus, so minus into minus plus. So the error is plus e power 1, okay? Similarly, if this is -1, but your prediction is 1, then also the error is high, right? So there is a question. Why would fm of x be plus or minus 1? Where did I say it's plus or? That. Okay, so we are just treating the target to be -1 and +1. Like you could do the same with 0 and 1, then the derivations are going to be different. So it's similar to like why we had +1 and -1 in the case of SVMs. So we just use either -1, 1 or 0, 1 based on our mathematical convenience. Okay, is the convergence guaranteed? I think so. I think so. So maybe let's discuss about that like once we go through the exponential error derivation. Okay, so now is the error function clear? Okay, so now once we have the error function, now the goal is to minimize this error function. Okay, now I want to minimize this error function for my classifier, but there is something different in this classifier when compared to the other classifiers that we have seen so far. Okay, so Krunal has raised his hand. I'm not sure if we have TA here. Yeah, Krunal, you can answer.
Can you explain again why is f actually plus or -1? It seems like it is just weighted sum of y. So what is restricting it to be taking like integer values?
Oh,
for example?
you meant that. Okay. No, then okay. So I think that's probably my mistake here. Just make this a sign. Okay. Hello. Okay, maybe you muted yourself. Is like okay, maybe type in the chat. Is that fine? Yeah. So I think it's easier for the derivation, like if we don't put the sign here. Okay, so I will still remove it. But when you want to use this classifier, you will use it as when you want to use this classifier for prediction, you're just going to threshold, saying +1 or -1. Okay. So now the goal here is to minimize this error function. Okay. Now, unlike other classification algorithms we have seen so far, in the case of boosting, you actually have to learn this alpha parameter, but you also have to learn the parameters of this classifier. Okay, so you have to learn two things. One, the weighing coefficients alpha L, and you also have to learn the parameters of YL of x. Okay, now instead of doing this in a global way, instead of trying to learn everything together, okay, we are going to take a sequential approach as I discussed in the beginning of the lecture. Okay, so we are going to take a sequential approach. Okay, where let us, like for example, let's say y1 of x to ym minus 1 of x. are already learned. We have somehow learned y1 of x to ym minus 1 of x. And also we have learned the corresponding alpha 1 to alpha m minus 1. Okay, now these are fixed. I have learned them and I have fixed them. Okay, so now I'm going to learn only the next classifier, which is ym of x and its corresponding coefficient alpha m. Okay, so these are the only things we are going to learn. Okay, now I can actually go back to my error function, which was summation over n is equal to 1 to capital N x of minus t of n fm of x of n, right? So this was my error function. So now I'm going to separate out the m minus 1 things from this error function. Okay, how am I going to do that? So I'm going to make this a summation over n is equal to 1 to capital N exponential of minus t of n fm minus 1 of x of n. Okay, and just put this final classifier separately. So minus 1 over 2 t of n alpha m ym of xn. Okay, so what have I done here? Like, so I just took the common error function. I divided it into two parts. The first part is the error if I'm using up to m minus 1 classifiers. And this is the error due to the mth classifier. Okay, so now you can see that this part, right? Okay, maybe that's the wrong way to do this. Okay, this part is constant, right? Like, because we are currently focusing on learning alpha m and ym, so this is constant. So I'm just going to call this as some w. Okay, this is how we obtain our weights. Okay, so now this becomes summation over n is equal to 1 to capital N wn of m x of minus 1 over 2 t of n alpha m ym xm. Okay, where WNM is the coefficient, which is given by x of minus t of n f m minus 1 of x of n. So I took the constant thing and I made it the weight. Okay, now this is my new error function. Is that clear? Okay, so now before we continue, like, I would like to simply divide this into two more terms. Okay, so let me go to the next page. So now let tau m be the set of all data points that are correctly classified, by ym of x. Okay, similarly, let mu m be the set of data points that are misclassified by ym of x. Okay, so now let's actually take this error function. I'm going to okay, so there's a question, why is first m minus 1 terms considered constant? Okay, so that is the setup, right? Like, so I'm learning each classifier sequentially. So, but when I'm learning the mth classifier, I have already learned the previous m minus 1 classifiers, so they are fixed. Is that fine? Okay, so I'm going to copy this thing. Okay. Okay, so look at this. So you have this error function, and like, I'm going to divide the examples into two sets, tau m and mu m. Tau m is all the examples which are correctly classified, and mu m is all the misclassified examples. Okay, if the example is correctly classified, then this term, right? So tn multiplied by ym, that is going to be +1. If it is wrongly classified, it's going to be -1, right? So I can actually simplify this by saying it's going to be e power minus 1 by 2, or it's going to be e power minus alpha m by 2, okay, summation over n belonging to tau m, wn of m, okay, plus e power alpha m of 2. So if it is wrongly classified, for all the examples which are in the wrong misclassified set, okay, there will be a minus, or minus into minus is plus. Okay, now this is, I have basically divided the error into two parts, like one for correctly classified set, one for incorrectly classified set, or misclassified set. Okay, so now I'm going to do a bit more like reformulation here. Okay, so I'm going to, I'm just rewriting this. Once I write this, you will understand that they are same. So e power alpha m by 2 minus e power minus alpha m by 2. Okay, summation over n is equal to 1 to capital N, Wn of m, indicator function, ym of xn is not equal to t of n. Okay, now this is not exactly same as the first term. I have added a bit more things. Let's see what I have added. So if you look at this summation, this indicator function is only for misclassified examples, right? So now for misclassified examples, you are multiplying by e power alpha m by 2, right? So now this multiplied by this whole thing covers this. Is that right? Now, we don't have anything covering the right examples. So what I'm going to do here is I'm going to add additional term plus e power minus alpha m by 2, summation over n is equal to 1 to capital N, Wn of m. Okay. Now this term covers this whole thing, but it also has extra, the incorrect terms, right? So now that is exactly balanced by this term. So I have done a little bit of algebra here, like so adding, subtracting things, but these two are exactly same. Okay, so the reason why I'm moving from the first to second is like now it is going to be very easy for us to differentiate the second one and set it to 0. Okay, okay. So now I'm going to rewrite the final error function that we have obtained, which is basically e power alpha m by 2 minus e power minus alpha m by 2, summation over n is equal to 1 to capital N, Wn of m, indicator function, ym of x of n is not equal to t of n, plus e power minus alpha m by 2, summation over n is equal to 1 to capital N, Wn of m. Okay, so now this is my error function. Now I want to minimize, our goal is to minimize this error function e with respect to ym of x and also with respect to alpha m, right? First, let's see how to do it with respect to ym of x. If you have to minimize this with respect to ym of x, then you can see that the second term doesn't contain any ym, so you can ignore it. This is a scaling constant, not useful in minimization. We can ignore it. So all you have to do is minimize this thing. Okay, so now you see how we get the boosting algorithm. So now to minimize e with respect to ym of x, my error function is given by just this term, summation over n is equal to 1 to capital N, Wn of m, indicator ym of xn is not equal to t of n. Okay, now this is exactly what the boosting algorithm is doing. So let's go back to our algorithm. Okay, maybe it's a lot of pages before. Okay, you see that for m is equal to 1 to m, you first learn the classifier by using this particular weighted error function. Okay, so now that also comes in our derivation. So it's exactly this one. Okay, so now let's move to the next stage. Like the next stage is minimizing e with respect to alpha m. Okay, so how to minimize e with respect to alpha m? So I'm going to probably take this and take it to the next page so that it's easy. Copy. Okay, I have my error function here. So all I have to do is dou E by dou alpha M. Okay. So e power alpha m by 2, if you differentiate it, you get e power alpha m by 2. Then you differentiate alpha m by 2, you get 1 by 2, right? So now I'm going to remove the 1 by 2 outside as a common thing, okay? So then you get e power alpha m by 2. There is minus e power minus alpha m by 2. When you differentiate this, you get minus 1 by 2, so it becomes plus, okay? Plus whatever the constant, you keep the constant as such. Summation over n is equal to 1 to capital N, Wn of m. Okay, to make things easy for me, I'm just going to put this as indicator I, okay? But you have to write the whole indicator function. Plus, you have e power minus alpha m by 2. You differentiate it, you get e power minus alpha m by 2. You differentiate alpha m by minus alpha m by 2, you get minus 1 by 2. 1 by 2 is already outside. So I just need to make this a minus. Summation over n is equal to 1 to capital N, Wn of m. Right? So now this whole thing is equal to 0. Okay, so now it's easy to simplify. So e power alpha m by 2 plus e power minus alpha m by 2, okay, times the summation over m is equal to 1 to n, Wn of m indicator is equivalent to e power minus alpha m by 2, summation over n is equal to 1 to capital N, Wn of m, right? So now just a bit of reformulation, summation over m is equal to 1 to capital N, Wn of m, indicator of ym of xn not equal to t of n, okay, divided by summation over n is equal to 1 to capital N Wn of m is equivalent to e power minus alpha m by 2 divided by e power alpha m by 2 plus e power minus alpha m by 2. Okay, so now we have seen this term already. Can someone tell me what was this term in the algorithm? Let's check your memory. No, this is not alpha. No, we have alpha already in the equation. This is the error ratio, error rate, right? Like, so this was our epsilon m in the algorithm, right? So epsilon m is equal to e power minus alpha m by 2 divided by e power alpha m by 2 plus e power minus alpha m by 2. Okay. Now epsilon m is equal to, now I can actually simplify this whole term. It becomes 1 by 1 plus e power alpha m. Okay. So the derivation is a small exercise. Okay. Now 1 plus e power alpha m is equal to 1 over epsilon m. Okay, I'm just going to continue the derivation here. So e power alpha m is equal to 1 minus epsilon m by epsilon m, right? So alpha m is equivalent to ln 1 minus epsilon m by epsilon m. Is that fine? So now, if you remember the algorithm, this is exactly what the alpha that we were using, right? So let's go back to the algorithm now. Let's go back to the algorithm and revise the algorithm again. So now we know where all these things are coming from. So first you initialize the data with weight of 1 over n, okay? Then for each classifier, you first learn the classifier by using this error function. Once you finish learning the classifier, you compute epsilon, then you compute alpha. Now alpha is the weight for the classifier. Then we still haven't figured out how this thing came, like how is this magical weight update happening, right? So to do that, let's go back to our derivation. Okay. Now remember that Wn of m plus 1 is equal to Wn of m x of minus 1 over 2 t of n alpha m ym of xn, right? So this is exactly what we saw in the beginning, right? Okay, so now we are going to use this property that T of n ym of x of n is equivalent to 1 minus twice indicator function of this. Okay. Now this is very easy to prove. Let's assume that the example is correct. If the example is correct, then this is going to be 1, right? Now look at the right hand side. It's going to be 1 minus the exam. Let 2 times indicator function will become 0 because the exam is correct. So this become 1. Okay. If the example is incorrect, this is for correct example. If the example is incorrect, then you have minus 1 here. So this becomes 1 minus 2, which is equal to minus 1 again. So these two are equivalent. Okay. So now we are going to use this and exactly substitute this term here. Okay. And you would end up with the formula that we had for the weight. So this is equivalent to Wn of m. Okay. X of minus alpha m by 2, x of alpha m indicator of ym of x and not equal to t of n. Okay, so now this term is actually constant. It's there for all the weights. So I could very well ignore this term. Now the rest is what the weight update equation is. Is that clear? Okay, so now what is this exponential error function doing? Okay, so can you repeat? So repeat which part? This one? Okay, so the last part is, okay, so earlier we found epsilon and alpha, right? Like, so the last part is really how to come up with the update equation, Wn m plus 1. Now, Wn plus n m plus 1 is given by this particular equation, right? So all I have done here is substitute ty with this particular version. Like you substitute this here and you derive things, you will get this. And I just noticed that x of minus alpha m by 2 is independent. Like it's same for all the examples. So I could very well, it's a common scaling factor. I don't need it, right? Like, so I just ignore it. And the rest is exactly what you see in the boosting algorithm. Okay. Okay. So now I just want to finish with like a brief discussion on what is this exponential error function doing. Okay. So why did I introduce a new error function? Like how is it different from the other error functions that we have seen so far? Okay. Now let's look at the expected error for this exponential error function. It is given by e x comma t is equal of x of minus t y of x. Okay, is given by the expected error function is given by summation over t integral over x of minus ty of x probability of t given x p of x d of x, right? So now if you remember our discussion of statistical decision theory, like, so if we want to find what is the optimal solution for this exponential error function, then all we have to do is differentiate this with respect to y of x and set it to 0 to see what is the optimal y of x, right? So what is del by del y of x of this exponential expected error function? Okay, now that is given by minus summation over t times x of minus ty of x probability of t given x p of x. Okay, so what have I done here? So e power minus ty, when you differentiate, you get e power minus ty, then you differentiate minus ty, you get minus t. Okay, so now this is equivalent to x of y of x probability that t is equal to minus 1x. Okay, so when t is equal to minus 1, this internal thing becomes just t, right? Minus x of minus y of x probability that t is equal to 1 given x. I have just expanded this summation. T is equal to plus 1 and t is equal to minus 1. Okay, So now we are going to set this equivalent to 0. So I know I'm running out of time, but I'll just finish in a minute. So we are going to just set this. Okay. We are going to set this equal to 0. So then it simply becomes exp of y of x, probability that t is equal to -1 given x is equal to exp of minus y of x, probability that t is equal to +1 given x. Okay, now this is basically exp of twice y of x is equal to probability that t is equal to 1 given x divided by probability that t is equal to -1 given x. Okay, now y of x is given by 1 over 2 ln probability of t is equal to 1 given x divided by probability of t is equal to -1 given x. Okay, now this is the optimal function for the exponential error. Okay, so what is exponential error trying to do? The exponential error is trying to model or approximate this log odd ratio, right? Like, so it's the ratio of probability of t is equal to 1 by probability of t is equal to -1 given x, right? Like, so now AdaBoost algorithm is trying to approximate this log odds, but we are doing it in a very different or unique way, because instead of doing it in a globalized optimization process, like we are doing it in a sequential way. Like we first learn the first classifier, then the second classifier, then the third classifier, right? So it's a sequential optimization. So now to summarize, like here you can actually see the mapping of exponential error function when compared to other error functions that we have seen so far, right? So if you remember, this is 0, 1 error, right? Like, so the red one is cross entropy. Can someone tell me what is the blue one? Yeah, it's hinge loss, right? And this is exponential. So you can see that exponential is kind of similar to cross entropy, but it penalizes the errors in an exponential way. So in some sense, it's an aggressive penalizing algorithm, which is also explaining why like boosting continuously improves, right? Like, so like you are aggressively penalizing and like you are trying to go to the right part, and you're doing it in a sequential way for different classifiers. Okay, so I think I will stop here. And like we're still not done with ensemble methods. Like, so we will see yet another ensemble method in the Monday's lecture. Is there any question before I stop the recording? Any questions? Kaggle will be announced by mail. There's no live session. Okay, so I will stop the recording.